Hello, my name is Jason Smith. I'm with CeramicSpeed, and we have just invented the world's fastest bicycle drivetrain. Come on, let's take a look. So, here's the concept drivetrain. Essentially what we did was we removed the chain, the rear derailleur, and the cassette cluster, and replaced 8 points of sliding friction with 2 points of rolling friction where the ceramic ball bearings engage the teeth. This originally started a year and a half ago with an internal project called the Pursuit of the 1% Drivetrain. We set a goal within CeramicSpeed to take a traditional drivetrain and somehow turn it into a drivetrain that would only produce 1% frictional losses, or alternatively 99% efficient. We had a good feeling that we couldn't take a standard drivetrain and just keep optimizing it, because that's what we do at CeramicSpeed right now anyway, and we weren't near 99% efficiency. So we started with a blank slate. We said, how can we get power from a rotational front axis to a rotational back axis with only 1% power loss? We had 10 or 15 different designs on the table, and something I must mention is we teamed up with the University of Colorado Mechanical Engineering Department, which was very helpful. So we had a team working on this. So we went through all the designs, and we figured that this would be the simplest design and give us the most efficiency. The way it works, now that you have the camera in there, is the bearings, those are ceramic roller bearings, interface with the teeth, and the bearings actually roll through the teeth. There is zero sliding friction that occurs, and the bearings actually index. So we do have a slight amount of rolling friction that occurs within each bearing as it engages. However, 2 points of rolling friction is much less than 8 points of sliding friction on a traditional drivetrain. Then it comes to weight. So that's the biggest advantage. And as far as numbers go, when we didn't test this prototype. We actually have a functional engineering prototype also. When we tested it, we found that this system creates 49% less friction than a standard derailleur style setup. And again, as I mentioned earlier, we did hit that 99% efficiency number with this system. It goes back to having 2 points of rolling friction rather than 8 points of sliding friction. One of the nice benefits of this that came along with this design was it's lighter than a traditional chain derailleur. What we did was we removed the chain, we removed the rear derailleur assembly and mechanics and cage, and then we removed the cassette. So we removed a fair amount of weight. Then what did we replace it with? We replaced it with a relatively lightweight carbon fiber shaft, and these would be carbon fiber pinions, and then a very thin single plane rear cog, which is lighter than the 10, 11, 12, 13 speed rear cassette. So all in all, we haven't done measurements, but we feel that this will probably be 15 to 20% lighter than a traditional drivetrain. Then, this is a 13-speed cassette. Another advantage of this system is we are not bound by the width of the cassette. So when you say, how many gears can you fit into a cassette? Well, it depends on how wide it is and how skinny your chain is. Because we shift in fore and aft rather than inboard and outboard, we just chose a 13-speed cassette. We could do 14, 15, 16. The only limiting factor is how far this pinion moves. So we could put 20 speeds in there if we want. And that leads me to how do we shift? Shifting occurs when this pinion slides forward and back, and it selects, in this case, one of the 13 gear rings. We have a cutaway here. This is how we envision the shifting would occur. We have a battery, the wireless electronics, the brain, servo motor, and the linear motion actuator. So this would be a fully electronic, fully wireless system, and something I just forgot to mention is we'd also put a power meter into the shaft. So everything would be fully contained, actually look like that, and very compact and very clean. Now when we shift, this can't shift instantaneously and randomly because we take out a lot of teeth. What would happen is the rear wheel, the rider would be riding along, a shift command would be initiated, and we have 5 shift channels. Here, for instance, here's a linear shift channel right here. Here is a parabolic shift channel as it curves through here. So we'd have a magnetic sensor on here, and depending on the rotational speed of the rear cog, the radial position of the rear cog, the position that this was in, plus the amount that it would have to move, the brains in the system, as it's spinning along, would know which shift channel to use to shift. Now that was a long explanation, but it would be relatively instantaneous to the rider. The rider would shift, boom, 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 boom. So it would be a fraction of a second between shifting, the shift initiation and the actual shifting occurring. Now we're getting into some of the maybe less important details, but they're still worth mentioning. Is this is an 8 bearing pinion and this is an 11 bearing pinion in the back. We did this to get gear increase out of it. By changing the pinion diameter, you can change the overall gear reduction or increase of the drivetrain, so you don't have to change the cog or the front ring. We envision at some point coming in, popping a release, pulling out the drive shaft, pulling the pinions off, switching pinions or putting completely different pinion diameters in, sliding it back in, slapping it up, and you're ready to go. So within a minute, you've changed the overall gear ratio of your drivetrain. So that means one day you have hilly races, put specific pinions in, and the next day you have a flat, faster race course, swap out your pinions. And of course, it looks really nice. Yet another beneficial side effect of this design. It's very clean, very sleek. You just don't have a rear derailleur hanging out there. You know? And I think that's it. Thanks for your time, and thanks for checking out the world's most efficient bicycle drivetrain.